Hello everyone, my name is Céline Pierre and I am the coordinator of the Processors and Polymers Master at IFP School. I'm pleased to give you this lecture on the plastics industry, after the petrochemical overview seen with Michel Duc. Today, you will be looking at plastics from the consumer's point of view, with plenty of plastic products available in the supermarket and in the house. In my first part, I will explain the exceptional diversity of plastics that made it possible to produce all these different consumer goods. Then, I will describe how they are manufactured. And finally, we will discuss the end of life and valorization of plastics. Around 300 million tons of plastics are consumed each year worldwide. In Europe, only 46.3 million tons are needed to meet that demand. They are now everywhere in our lives, since their discovery a few decades ago. A huge amount is used in the packaging sector to protect the final product after manufacturing and during transport to the supermarket, and finally to the customer. In Europe, in 2013, this sector covered 40% of the plastics manufactured. The second most important application is for building and construction, almost 20%. We, as consumers, may recognize some plastics thanks to an identification code, quite common worldwide now. However, it's not compulsory for the plastic manufacturers to stamp it on their products. Several codes exist, as shown here. Take some time to read them. But first of all, what are plastics? Well, first, let me introduce some vocabulary. Remember the reforming, FCC, and steam cracker units seen with Michel. They produce some small molecules, the petrochemical intermediates, such as olefins and aromatics, shown here as M. The next step is to add them together, the so-called polymerization step, in order to build a very long chain with a successive arrangement of repeating M units called the polymer. Then, some additives, bringing resistance to oxygen or to UVs, may be added to polymers. After this step, we obtain mixtures called plastic compounds, most often available in pellet form. They have now to be converted to the final object. This is known as plastic material processing. And last, after being filled with soap, water, food, etc., the end product is sold to the customer. Since we are able to combine different types of base chemicals, we can manufacture almost as many polymers and plastics as we want. This was made possible thanks to innovation that meets customer demand. Customers first is the rule in the plastics industry. It's the job of a product development engineer to launch a market study to identify customers' needs. As an example of constant innovation, we can take a look at the increasing part of plastics in aircraft manufacturing. In this sector, innovation always looks to reduce the overall weight of the aircraft, while maintaining high mechanical strength. Composites, which are a mixture of plastic and carbon fibers, meet this need. They are used for around 50% of all materials. Let's move now to the manufacturing of these polymers and plastics. We have chosen to show you some common polymers with very high production quantities and low prices. They are what we call commodity polymers. Let's remember first the simplest base chemicals from the reforming, steam cracking, and FCC units. These olefins and aromatics can be in the liquid state, like benzene and xylene, or in the gaseous state, like ethylene, propylene, and butadiene. Let's start to operate our plant. This is the job of a process and operations engineers. Ethylene and benzene can react together to give styrene, a petrochemical intermediate. The chemical formulae are shown here to illustrate the change inside the molecule. Then, in a last step, styrene can be polymerized with itself to give polystyrene, so-called PES, used to manufacture yogurt pots, casing for cities, insulation for houses, etc. Starting from styrene again, instead of polymerizing it alone, we can make it react with butadiene, resulting in a polymer called styrene-butadiene rubber, so-called SBR, used for tires. Let's come back to ethylene. This base chemical can be chemically modified into a petrochemical intermediate called ethylene glycol. The chemical reaction between ethylene glycol and xylene will produce the polymer we call polyethylene terephthalate, PET, widely used for soft drink and fruit juice bottles. But the same polymer can be converted to another form to produce polyester fibers used for clothing. As a final example, going back to ethylene again, it can react with chlorine extracted from salt to produce vinyl chloride. Polymerized with itself, it can be used to manufacture polyvinyl chloride, widely used in the building and construction sector for window frames and water pipes. Let's finish with the last two base chemicals, ethylene and propylene, which account for the largest volume of olefins in the world. Ethylene can be polymerized with itself. Depending on the reaction conditions, final polymers can be low-density polyethylene, LDPE, or high-density polyethylene, HDPE. They do not have the same purpose. On the one hand, LDPE is used for transparent, flexible packaging for water bottle packs or bags. On the other hand, HDPE is used for milk bottles, cleaning agent bottles, shampoo containers, etc. Propylene can also be polymerized with itself, resulting in a polymer called polypropylene, used for car bumpers, but also for takeaway food containers and lunch boxes. So, we've seen in this part how we manufacture some polymers. Let's move now to plastics. Basically, all the plastic compounds are in solid form and will flow, like honey, when you increase the temperature. During the processing step, the polymer will pass through the equipment. Once you reach the desirable shape, the product is cooled down to keep the right shape. One example of processing is the thermoforming process, where a hot plug punches a heated plastic sheet into a mold. Once the mold is released while cooling, the plastic keeps the desired form. This is the case for PS, meat packaging, as seen in the picture. A second example of packaging is injection blow molding for water bottles. An initial piece of plastic, called a preform, is introduced into a mold. It is then heated and air is blown into this plastic preform, which grows until it reaches the walls of the mold. Then, the mold opens to release the plastic. Of course, the choice of a process depends on what the final product will be used for and on the properties you want to obtain. If we focus on packaging properties, we first need our plastic to resist shocks. We first have to assess a high mechanical resistance, which is possible with PET and HDPE. PP is also used, for example in caps, which have to be opened and closed very often. On the reverse, for some applications, we prefer the plastic to break easily, like for the yogurt family pack manufactured with PS. So be careful, don't drop them. Another kind of property is the ability of the plastic to resist UVs, milk bottles for example. In this application, there are successively 3 layers. An outer white one in HDPE that brings mechanical strength, one dark one to resist UVs, and the third white one, the inner one, that forms a lining because the customer does not like to see a black color inside the bottle when he pours milk for breakfast. Lastly, for packaging, some optical properties can be desired. The product looks more tasty or luxurious if the plastic is highly transparent, like PET, or even glossy, like PP. Good examples are fruit juice bottles or individual yogurt pots that can be more attractive for a customer than a classical and inexpensive yogurt family pack. Now, let's move to the end of life of plastics. The advantages are to be light and durable, which is a problem for the environment, especially if you throw them away. In Europe, in 2012, as shown in this graph, 25 million tons of plastics were collected. 36% were burnt to produce energy, 26% were recycled, and another 38% were sent to landfill. It is no longer acceptable to bury our rubbish, and the objective to reach 0% landfill in Europe before 2025 is possible, but only if everyone takes action. Retailers who decided to ban single-use bags are making their contribution. One possibility to reduce plastic waste is to promote mechanical recycling, as for PET bottles. After being sorted, crushed and separated, flakes can be melted and used to manufacture either films, fleece jackets, and new bottles. In recent years, they have developed some new plastics to face environmental challenges. 2 new trends have appeared. First, instead of recycling or burning them, new plastics can be biodegradable. Second, to reduce the use of oil, they can be manufactured from biosourced materials. Both types of plastic already exist and will be further developed in the coming years. So, in this presentation, we've seen the end of the petrochemical chain, with the manufacturing of the plastics that are present in our everyday lives. As a conclusion, we can say that the diversity explains the success, but, on the other hand, the complexity also makes them difficult to be collected and sorted. So, that's all from me for the moment. I leave you now to play the serious game. Have fun. Bye.